we will head into the next topic, which is the design. So here are two different controllers. One is feedback linearization. Another one is high gain controllers. So let's go to this topic, feedback linearization. So given a dynamic system described by x star equal to ax squared plus u. U is the control input to be designed. A is a non-positive constant, for example 1 or 2 or whatever. If you don't design any control, the open loop dynamics is x star equal to ax for u equal to 0, right? If you don't give any control. And that will be an unstable system because this is a phase portrait. Okay, it's a one dimension because x is a scalar. If you put u in each condition here, the system trajectory will try to go to the right. Okay, and it won't stop at the origin, so it's not stable. Or you can even solve for this nonlinear ODE, right? It's possible to solve this. Again, you can find the solution is not stable. So the next question is how we can design the controller to stabilize this system, to change the phase portrait, and make every solution will converge to the origin. Again, A is a non-constant, but usually in the physical system, for A we will call its parameters, the parameter of a system, which implies, for example, if this dynamics is trying to describe the car, A could be the mass of the car, and A is a constant. Imagine if you know the mass of the car, then you know how to design your control input. For example, how much gas you need to put into the car to generate some desired acceleration. So how will you design these controllers? And here the approach we introduced is called feedback linearization. Feedback is fine, but what is linearization? Again, this is a nonlinear dynamic, square x squared, so it's nonlinear. So we're trying to find a controller U that change the phase portrait of this open loop dynamics. Okay, so we're trying to design U such that the phase portrait becomes this, which is stable around the origin. So what's the controller looks like for this dynamic system? So for this phase portrait is plotted according to this dynamics, which is a linear dynamics. X star equal to minus x, so it's stable, right? So after you design U, okay, you substitute U here, maybe this one will be canceled out. And another second term in U will create this minus x, so that the overall system becomes to this dynamics, which is stable. And that's called feedback linearization. So originally dynamics is this. This is open loop dynamics because no control. Now you have a control U, and it's nonlinear. Okay. Now you want to change the open loop dynamics to some desired dynamics, which is x star equal to minus x, because we know it becomes linear and most important is stable. How did you design this? U. So it should be easy, right? You need to design a U that cancel out the first term, right? So you put a minus sign here, minus of this, which is minus ax squared. Okay. And minus x, which is for this. And this cancel out this term. 能懂吗? So easy, right? But it's not problematic because usually we don't know A. We don't know what's A, right? Back to the example, the car example. Given any car, if you don't measure the parameter, you don't measure what the mass is, usually it's unknown. And sometimes time variant, it's changed all the time along the way, right? In addition, for the car dynamics, not just mass, it has inertia, some other parameters. So assuming that A is a non-constant is not realistic. If someone told you that I use a feedback linearization controller to stabilize the system, usually is not, that's problematic. Okay, it's usually not applicable. You can ask him, how do you know your parameters? That's the first question to ask. Okay, and the answer will be, problematic. But the advantage is once you can change your open loop dynamics to this closed loop dynamics, which is linear, it can evaluate the performance, right? You can always solve the solution of a linear ODE, right? So you know how fast you will converge to your desired, how fast it converges to your origin or to the equivalent point. 这样知道？ Start from now, we will discuss controller design. How you, given the nonlinear dynamic system, how you design the controllers according to different conditions like unknown parameters or with disturbances. First one is feedback linearization, okay, and second one is high gain controllers. The A here is assumed to be a non-constant, okay, which implies you have the exact model knowledge. You know what the inertia is, viscosity of the system is, if any. And with the model knowledge, it's easier to design the controller U. And this is the open loop dynamics where you don't apply any control input, right? So it is zero. And this is the dynamics, which is unstable. And after you apply a control input U, you design a controller and substitute into the system, you got this closed loop dynamics, okay, which is stable. And this is the objective of designing the controller that stabilizes the system, which might originally be not stable. So the controller for the previous slide consists of two components. First component is to cancel out this nonlinear term in the dynamics. This one can be canceled out because A is known, right? Because remember this, everything in your controller have to be known. Otherwise, how can you implement the controller? Everything in the controller have to be known. Everything on the right-hand side have to be known. So your state has to be measurable. Your system parameter have to be known. Otherwise, you cannot implement the controller. And because we know the model knowledge, so we can design this controller. And this component cancel out the nonlinear term in the dynamics. That gives you this closed loop dynamics, which is linear and stable. So now let's prove this. Is this system, this closed loop system is stable? Or what's the stability of this closed loop system? Okay, so we can prove by using the above function approaches. You select the above function quadratic form. When you take the time derivative, right, then you can substitute your closed loop dynamics from here. And the result is NSD, right? Here you have x squared and here's minus x squared. So PD and ND. So the conclusion is RU, right? So it's globally asymptotically stable. And can you further discuss the convergence rate? So here what I did is I took this, which is this, and we can find the relation between x and v. The relation between x and v is this. So you replace this x squared by 2v, Then this becomes a linear ODE, and you can solve for the solution if the initial condition is known. So what's the benefit of solving this? Well, it's easier to see that it's globally exponentially stable, right? Because V, given some initial condition, this V decays exponentially fast. And if V decay exponentially fast, so did X. So the defect is it requires model knowledge. Second example is Now we add another nonlinear terms. Again, we follow the same procedure for feedback linearization controllers. As you added this in the dynamics, you want to add the same term with a different sign, right, in your controller, as to cancel out this in the open loop dynamics. The closed loop, after you substitute this into the open loop dynamics, you can get the closed loop error system. And again, it's stable. It's globally exponentially stable. So let's discuss this. What's the defect of feedback linearization controllers? Other than it requires model knowledge, okay, the good terms will be canceled. What is good terms? This is good terms. You know why? V dot is x. So if you substitute the open loop dynamics, okay, this is open loop dynamics, and closed loop dynamics. Okay, V equal to, okay, why do I call it good terms? The reason is when you substitute the open loop dynamics into here, okay? Let's take a step back. So which is ax squared minus x cubic plus u, right? And you expand out the whole equation. You got ax cubic minus x power to the fourth minus xu. Okay, this is v dot, right? So the contribution of x minus x basically is it comes to minus x power to the fourth, right? So this term is always negative. It's always negative. So this term can help v dot to be more negative, right? No matter what x is, right? So if you put if you keep this term, okay, if you keep this term, v will converge faster. So and in the controllers, we design this term to cancel out this term, which is a good term, so that the convergence rate of v dot is compromised. So if the controller is compensate a wrong term, it's better to keep this term. Okay, so let's try this. Now we refine the controllers from u equal to minus a x squared plus x cubic to u equal to minus ax squared plus x. We don't want to cancel out this, so I just kick this term out of the controller. Okay, so if I substitute this into the open loop dynamics, what will the stability analysis look like? So let's try. If you substitute this back to the open loop dynamics, that gives you what? Closed loop dynamics. The new closed loop dynamics becomes what? X dot equal to a squared minus x cubic plus minus ax squared minus x, right? And these terms cancels out. That give you, right? So this term have been recovered, okay? So let's try substitute this into the v dot. So v dot is x dot, okay, which is x, and substitute the closed loop dynamics into here, which give you right? So compare with this term. Now we recover this term. So it's still negative definitely, right? For sure, right? But it even converge faster than this, okay? And compare with the controllers, okay? Compare this controller and this. If you now say x equal to 1, okay? Initial condition. If you start from the state that equal to 1, and let's try to substitute this into the two controllers. The one on the left hand side give you what? Minus A1, okay, 1 square plus x 3 minus 1, okay? And the one on the right is what? Minus A1 square minus 1. So it's not a good example. Maybe try minus 2. Let's try minus 2. This is minus 8. Okay. So what's this? It's 8 minus 2. Okay. So compare this. See, given the same state, this is the control output. This is the control output. Which one is larger? In terms of magnitude, this one is much larger, right? Magnitude. Okay, so it requires more power, right? If the control system is a robot arm, right? The control means the voltage to the motor. The requirement is larger to drive or to stabilize the system, given this controller, right? So it requires more power, more powerful controllers, but this one is not. That's the drawback of feedback linearization. Or maybe you can avoid this situation by observation. If you see it's good terms, you just keep it, okay? You don't want to cancel it out. So in conclusion, design procedure is this. Given a system structure, x star equal to ax plus b gamma x. Gamma could be some nonlinear function. Okay, gamma x could be like x cubic. So the controller design is you design u equal to alpha x. Alpha x in u will cancel this out, and the other term, this one, will multiply with this, which is the inverse of gamma. Right? So it becomes 1. So the closed loop system will become kind of like a linear system. And since it's kind of like a linear system, you can design this new controller by another linear approaches like pole placement. So remember, cancel some nonlinear term from open loop dynamics and add some linear term here. Not necessary to be linear, okay? But the closed loop system could be linear. And everything here had to be known. You had to know what is alpha, what is gamma function. You have to know what is gamma, what is alpha in the open loop dynamics. Otherwise, you cannot apply this approach. So this is the first controller that we introduced. For sure, it's probably the most simple controller design. So the next one is how about consider the unknown system parameters. A is assumed to be unknown. Okay, in the previous case, it had to be known. What if A is unknown? Then you have two options. Option 1 is you design high gain controllers, and it's also called robust control. Or option 2 is adaptive control. You don't know the system parameter, but you put the estimate of this unknown constant in your controllers. Somehow stabilize the system. And the stability can be concluded as asymptotically stable. So we will discuss option 2, the adaptive control, later. We focus on the high gain control now. So what is high gain control? So I give an example. Given this dynamic system, okay, x star equal to theta, which is a unknown constant, sine square t plus plus u. So theta is some unknown parameter, which is a constant. So for example, theta is the mass of a system. Okay, we don't know the inertia of the system. What is known is its upper bound. Theta can be a positive constant, negative constant, but no matter what, we know its upper bound, which is upper bounded by C. And you can design some robust controller. Here, the structure is minus kx. This is linear, but this is the robust controller. The design procedure will be backwards. We first follow the stability analysis and see how you can design this VR, this robust control, from the analysis. So we take this open loop dynamics into analysis. Okay, we take this dynamics into analysis. We design this therefore function and take the time derivative, and in which you can substitute your open loop dynamics. You substitute the controller here, okay? Minus kx plus VR. VR is still to be designed. So if you design VR as minus k2x and you substitute minus k2x, you got this. And you expand this out, minus kx and x. So it's minus kx squared and minus k2x squared. So basically for now, this robust term is similar to this. It's minus kx and this is minus k2x. But the selection of k2 will be different. There's a trick here. Here's the equal, right? But here is upper bound. What happens? How can you modify equality to an inequality? Do you see the difference? This term and this term remains the same from previous one, right? What is different is this. And is that true? Can you use this term to upper bound this term? Anything wrong with this? So here what I did is I upper bound this term to this term, right? If you can find a counterexample, which means you agree with this result, right? So this procedure is correct. Why I need to upper bound this? So think about this. This is state, right? Do you know what's the value of state? We don't know. We don't know the trajectory. Given this, we don't know the solution of x, right? So we cannot guarantee what x will be. And if x is always positive or is always negative, it's hard to say, right? But here is always positive. It's always positive. But here could be positive or negative. Our objective here is to ensure veta will be negative, right? Veta to be negative definite, which means the right-hand side of the inequality had to be negative. But here, the problem is this term, the product can be sometimes positive, sometimes negative, right? But we want it to be negative, but it's impossible because it could be positive or negative. You cannot predict what the state will be unless you know the solution. Right, but it's in nonlinear dynamics. You don't know the solution. So you need to consider the worst case. Worst case means what is the largest value of this? You want it to be negative. So worst case is what is the largest value of this? So you can say for A and B are any real numbers, could be positive or negative. You can upper bound this by A, B, as the value of AB, right? It's always true, right? 对不对？是吧？ Because the range of AB is this, right? And the worst case is this, right? This is the worst case. So that's here, this term. The last term is the worst case of this product can be. This can be further upper bound by this. Right? This can be further upper bound by A, B, as the value A times as the value of B. And the worst case of this term, this product, will be C, X, as the value of X, right? C is a positive constant, right? Which upper bound this. So sine square is always go from step by step. And this, the worst case of this is 1, right? This remains the same, theta here. So theta here, right? And theta here. And theta here, okay? And using the condition that we know theta, we don't know whether theta is positive or negative, but it can be upper bound by some constant, positive constant C. So now you can substitute c into here. So it's cx as the value of x. So next, we combine these two terms. So you move absolute value of x out of the bracket. And now, so it's always positive, right? As long as everything in the bracket is positive, this whole term is negative. And we can drop out the terms. Okay. So it becomes v dot equal to, will be upper bounded by minus kx squared. Okay, v dot upper bound minus kx squared if this term is positive, if this is greater than c. So from here, it's globally uniformly stable. Why? Because you won't converge to 0. When you see this, you cannot say it's negative definite, because as x trying to converge to 0, when x trying to converge to 0, this term will be 0. But it's a constant here, it's a positive constant. So eventually, this term will go from positive to negative. And the second term will go from negative to positive. The intersection will be where x equal to, so v dot will be upper bound by some negative definite function if this is satisfied, right? But when x is equal to, you move this to the right, k2c. When x, absolute value of x is equal to this constant, this will become 0, right? And it no longer holds. 这个成立只有在这个条件下成立的时候嘛，那这个不会一直成立嘛。When x 变成是这个 value, x could decrease from some initial condition, right? And decrease to 0, trying to decrease to 0. So when it getting smaller and smaller, probably at these values, this condition never holds. And this condition breaks. And that's why it's globally UUB. It will eventually be bounded. It cannot converge to 0 because of this term. Maybe you can think it another way. What if x equal to 0? What if the objective is prove x converge to 0, right? What if x equal to 0? This is 0. Or if x is a very small value close to 0, so it's almost 0 here, right? And so everything in the bracket is like a minus c, is a negative value. So this second term is positive. And the first term is almost 0 because x is around 0. So the whole term is positive. V dot is positive. What happens when V dot is positive? It's not convergent, right? So it never converges to 0. X never converges to 0. So if we plot this, basically when you start from V0, where x, okay, start from 0, and it goes to 0, but it never reaches 0 because of the uncertainty, because of the second term. So eventually, it reaches to some UUB, okay? Okay, it cannot be 0, otherwise V dot will be positive. So this term, the objective to keep this term is to make sure V dot is upper bound by some negative definite. And in which case we can say V dot is negative. That's only true when the second term is also negative. If second term is positive, it over-dominates the first term, and the overall product is positive. We want V dot to be upper bounded by some negative value, right? So first term is negative value, okay, but this term can be positive. And once it goes positive, V is no longer decreasing. So the problem is this term, the second term can be positive. But when, at which x it will go positive? This x, when this summation is 0. Absolute value of x equal to this, that's the time that V start to decrease. 虽然它前面还有这个嘛，但是 worst case 是这样。You can merge these two terms. You can merge k plus kx squared. So we want this to be negative definite, right? want this to be negative definite, but it's not always negative definite. For example, when k plus k2x squared can this be 0? It can, right? Then when x norm is 消掉一个 c when x equal to ck when x absolute value of x equal to this value, this becomes 0. So which means it stop decreasing, v start decreasing. But x is not haven't reached to 0, right? It's not equal to 0. So before it goes to 0, v start decreasing, which means it's UUB. Why it doesn't converge to 0? Because of the uncertainties. Because of this c. If c is 0, if you observe c is 0, then this will be 0, right? So it will converge to x, the absolute value of x will be 0, and v dot will be 0, which means it converges to the origin, right? But because c is non-zero, it comes from the uncertainties, okay? So if you have uncertainty in your dynamics, and you use high-gain controllers, then it won't be globally asymptotically stable. If you don't have unknown in your system, how can you control something unknown to be asymptotically stable?